Homework questions? Nope. I think I should be able to get the test back on Thursday. All right, so what were we talking about last time? Okay. Mm-hmm. And after that, we got into the new topic, which was friction, right? So we started friction. Mm-hmm. There we go. Started friction. Um, and we're breaking this up into three pieces. First, we're talking about square threaded screws. That's what we're working on right now. And second, we're talking about belt friction. And then third, we're talking about bearing friction. And we're going to break that up into, I don't remember what order I gave this in, but journal bearings, and thrust bearings. Okay, so what are these things, first of all? Did I what? No, I couldn't find them. Yeah. She's been nothing but trouble for our department ever since she came here. Yeah, exactly. First minute you talk to her, you can tell. Um, okay, so what are these things? So square threaded screws, that's what we're working on right now. That's as opposed to, well, what I think of as just standard screws. Square threaded screws are harder to manufacture, but they're better at supporting big forces. Belt friction is like so imagine this is like a rope coiled around a post. On this side of the rope, you have some tension T. And on this side of the rope, you have, well, let's call it T2 over here, T1 over here. So if you're trying to use this rope to provide a big force, say T2 is the big one, you could supply that force T2 by pulling on the other end of the rope T2, right? Or you could wrap this thing around a post or a beam or whatever, and that friction takes some of that force. And so if you do this, you can support this force T2 with a smaller force T1. So that's the idea of belt friction. And that friction is going to depend on how many times it's wrapped around. Then bearing friction. A journal bearing
is like a bearing supporting a spindle. So if this spindle or axle is rotating,
and it makes a joint with this, that's like a pin joint. This thing rotates in there, but at the contact point, there's friction that provides some set couple. And because of the couple that's applied to the axle by the support, by the bearing, in order to keep this rotating at a constant speed, you need to supply some fixed couple. If there was no friction there, any couple you applied would make it have an angular acceleration. But because of the friction, you need that just to keep constant angular velocity. So that's a journal bearing. Stop me if you have any questions about trying to picture these or anything. And then the last one is a thrust bearing. And that's like the friction on the end of your cigarette when you're stubbing it out in your smoking room, It's like okay, well, when you stub out your pipe. I don't know much about pipes. Okay, but this is so thrust bearing is like if you have shaft that's rotating like this, and it's in contact with, say, the ground like this, in order for there to be friction, actually, there has to be some kind of force. I'll call it P, pushing down. But this force pushing down makes there be friction between the bottom of the shaft and the ground, and that has the same effect as this. To keep this rotating with a constant angular velocity, you have to apply some fixed couple. So those are the 4 types of friction that we're dealing with. Okay, so we're dealing with square-threaded screws. And I said that there's an equivalence between, so if you have a square-threaded screw that you're trying to this picture is not helpful. Well, if this is your screw and it's supporting some weight that I'll call W, and if you're trying to get that screw to lift, if you're trying to apply the load required to lift this, you have to apply a couple. I'll call it M. That's how you turn a screw. You apply a couple to the screwdriver or to a handle of some kind. And there's an equivalence between this, where we're trying to lift this screw, and a simple block on an incline problem where we have W acting down and Q fighting against the that weight W. Can you see what I mean by whether Q is fighting against that weight W or working with it? So if we're trying to lift this screw, we're trying to get that screw to move, and that weight would help us somewhat in trying to get this screw to lower, but it's fighting against us getting it to lift. And so in this case, we need to apply a cue that, that pushes it up the ramp in the opposite direction of that weight. And there's also then the equivalence between, so if we have this screw, and there's the nut or whatever it's articulating with, and we have the weight W. In order to get it, you know, because of friction, well, we wouldn't want this to be friction free. We're using that friction to hold our position. You know, the last thing you would want is a screw that you turn it a quarter turn and reach to turn it again, and it drops back down to the bottom again. What? It could be kind of fun, that's true. But to get it to go down because of that friction, you also have to apply a couple. It would be in the other way, other direction. So to lower it, you have to apply a couple like that. And that is equivalent to a box sliding on an incline with weight like this. And this time you're trying to push it down the hill with its force cue. Okay, so today what we're going to do is we're going to we'll talk about solving that problem, that block incline problem. And let me put this angle in here because this is always the angle that we're going to be dealing with. So let's call that angle theta. So the first thing we're going to do is solve that problem, which you did in Physics 1. Second, we're going to talk about a relationship between, so notice that in the real problem, when we're talking about that screw, the load that we have to apply to either lift or lower this screw comes from that couple M. But in the simplified problem, the block incline problem, that couple is related to force that we apply Q. Okay, so the second thing we have to talk about is the relationship between the real load M and the, you know, just mathematical, I don't think quotes are really the right thing here. But relationship between the real load M and the mathematical load that actually isn't a physical thing that we apply, Q. And then the last thing we have to talk about is if you go into a hardware store, you should do this after class today. Go to the hardware store and tell them you need a screw where the threads are at an angle of 11.6 degrees or whatever. You know, they'll think that's good and funny. So the parameters that are listed for screws are not angles. And so we have to talk about a relationship between the pitch and the lead and that angle theta. No, talk to the grown-ups. Talk to their manager. Okay. The relationship between or lead and that angle theta. No, theta. Question? Oh, you could have done that. Dang. Shoot.
All right, so here's the example we're going to do.
I'm going to do it all symbolically, but the problems that you'll have to do are all going to have the numbers included.
And by the way, with all of this stuff, I want you to remember there's one of them, the belt friction. I'm going to sort of give you a formula, and that's that, because the derivation is pretty messy. But for the other three types of friction problems, I'm going to expect you to be able to follow through a derivation like this. You can plug the numbers in, but I expect you to remember how this works. You won't just remember the formulas, you know. Okay, so let's say we have an incline with an angle theta and a block with a weight W applied. And we want to know what Q is required. Oh, and also there's friction here. I'm going to just call this the coefficient of friction. You can do these problems as static friction problems or kinetic friction problems. The static friction problem would be what's the Q that you have to apply to initiate motion, and a kinetic friction problem would be what's the Q you have to apply to keep it moving with a constant velocity. But mathematically, they're the same problem. You just use a static or kinetic coefficient of friction. So Q is required to initiate motion against the load. Usually that load would be some kind of weight, and so we're talking about moving the screw up. And then second, what's the Q required to initiate motion with the load? So down. Okay, so part A. A free body diagram of that box. There's a weight. And we're lumping the weight of the box and the force applied to it into this variable W. Remember, so what does this box represent physically? Yeah, and basically it's kind of lumping the whole thread together. So when we talk about, you know, normally when we're doing a free body diagram, we'd put mg in there, but we'd be talking about mg of the thread of a screw compared to like this large load that's applied. So usually the thing that's applied to it is the only significant force. So anyways, weight is like this. And then there's a normal force. And there's a friction force. Which way would the friction force act? Yeah, we're trying to get it to slide up, and that means the friction force is going to slide down the incline. So there's a friction force like this that's equal to mu n. And then which way would that force Q have to act? Left or the right? To the right, yep. So there's the problem. When you did this in physics 1, I think, the way you probably did it. So what are the things that act in a single component direction, and what are the things where we have to use trigonometry to represent the components? So what coordinate system did you use for problems like this? I guess that's sort of the key. You're like, I don't know, my friend took my test. Yeah, with the incline, yep. So the y-axis pointed out, the x-axis pointed like this. Okay, so in that rotated coordinate system,
this is in the positive y direction, this is in the negative x direction, and then we have to use trigonometry for these two.
and so you might have set it up like this. So let me show the weight. So if that's the weight, you broke it up into a component like this, plus a component like this. This angle was theta. So if this is W, then this is W cosine theta, and this is W sine theta. And then
You can just think about the quadrant.
let me draw the coordinate system.
So that weight is in the third quadrant, so you know both of these components have to be negative.
So you can do it like that. I want you to notice you can also use rotation matrix for this. And when you're used to rotation matrices, this is just a nice quick thing. You just plug it into your calculator and you're done. So that's how I'm going to do it. No, not in this case. It would be the x component if
Your theta went all the way from the positive x-axis to this vector. So if instead of calling this angle theta, your theta was, well, so this component would be W cosine of 270 minus theta. And then you wouldn't have to think about the signs of it at all, you know. And then the y component would be W times sine of 270 minus theta. And then you don't have to think about plus or minus. That's sort of a nice benefit of that. Symbolically, the nuisance is then you have everything in terms of 270 minus theta instead of theta. You could use trig identities to simplify it, and you'd get this. Okay, so let's think of it now as a rotation matrix thing. So notice that W and Q, okay, so you can do this as rotation matrix calculation. Because in a coordinate system like this, Q and W are very simple. That W vector is just 0, negative W. And that Q vector is just positive Q, 0. Now, if we use a rotation matrix just to transform these vectors from this coordinate system into that rotated one, then we're done.
So the rotation matrix that goes from this to this. Yep, plus theta. And so the rotation matrix is cosine theta, sine theta, negative sine theta, cosine theta. That's the rotation matrix. Oh, geez, we have those two Q's. Don't put that. So that's the rotation matrix. Okay, so then in our rotated coordinate system, our W vector is just cosine theta, sine theta, negative sine theta, cosine theta, times 0, negative W. And so you get negative W sine theta, negative W cosine theta. And obviously that, that took a lot longer if I'm explaining all the steps and doing this multiplication by hand. But if once you're used to using rotation matrices, you already have it programmed into your calculator. That's just, entering a couple numbers, no thinking. And that's always our goal. And then that Q vector is the rotation matrix, same rotation matrix. Times Q0. And so that's Q cosine theta, negative Q sine theta. Done. Okay, so now that we have all that, we can write Newton's second law. Go back up to this free body diagram. So we have the Q vector that we just calculated. Q cosine theta, negative Q sine theta, plus the weight that we just calculated, negative W sine theta, negative W cosine theta, and then normal and friction. The normal is 0n. The friction was in the negative x direction. So that's negative mu n 0. And how do we know what the right side of this equation is? I mean, really, we know because this class is called statics. So acceleration is 0 in every problem. But we're talking about what force do we have to apply so that this thing is still at rest, but if you applied any more force at all, it would start to move. And so we're still talking about the static case and to calculate this Q. So 0, 0. Okay. And then how do you calculate Q? So now it's just algebra. From the second equation, you get that n is equal to Q sine theta plus W cosine theta. And then plug that into the first equation. And you get Q cosine theta minus W sine theta minus mu times the quantity Q sine theta. So I'm substituting in for n now. Q sine theta plus W cosine theta is equal to 0. I'm trying to calculate Q, so let me just multiply this out. So Q cosine theta minus W sine theta minus Q mu sine theta minus W mu cosine theta is equal to 0. And I'll group the Q stuff on the left side. So we have Q times the quantity cosine theta minus mu sine theta is equal to, I guess I'll write this as W times the quantity sine theta plus mu cosine theta. And then divide and you get that Q is equal to W times the quantity sine theta plus mu cosine theta divided by the quantity cosine theta minus mu sine theta. Okay, so that is a formula that, you know, you could just memorize what the, remember what that's applicable for, use that formula in the future and it would work, but I want you to be able to do that derivation or something like it. So now we're going to do the other case. Any questions about that derivation? So that's the answer for A. If that's your coefficient of friction, that's your angle theta, that's your weight, this is the Q you have to apply to get the screw moving against the weight. Now in B, we want to get the screw moving with the weight. So what's the Q required? So the screw moves with the weight. Well, is this going to be bigger or smaller? Yep, does everyone see that? The question is basically, do you have the weight helping you get it moving, or is it making it harder to get it moving? In A, the weight was fighting against what we were trying to do. In B, the weight is helping us, and so we should be able to look at the answer and see that the value has to be smaller for B. Okay. And this is a spoiler. The way it's going to come up is these signs are going to switch. This is going to be a negative up here, and this is going to be a positive here. And so the effect of that is, for part B, making the numerator smaller and the denominator bigger, and that makes Q smaller. Okay. Anybody want to try this? You want to try to do it? On the board? Fred, you want to do it? That would be pretty cool if you did just go up and do it. Okay, well, I'm going to do it then. I don't want to do it either. No one asked me. Yes, you make a good point there. Okay. Okay, so free body diagram. We have the weight. That's W. We have the normal force. And then we have the two things that are going to change. What are those? Q is going to go the other way. Yeah, and so the direction of Q changes and the direction of the friction changes. Now we're trying to get it moving down the incline, so Q goes that way. And since we're trying to get it moving down the incline, the friction acts up the incline, so that's mu times normal. Well, it's the same deal, rotation matrix, so our weight vector is equal to cosine theta, sine theta, negative sine theta, cosine theta, times what we're doing is we're using this rotation matrix to transform vectors from a standard coordinate system to the rotated one. So what would the weight be in a standard coordinate system? 0, negative W, yep. The weight is the same, yep. Exactly. So we still get negative W sine theta, W cosine theta. And then Q, this one is going to be different. We have the rotation matrix. Times, what's Q in the standard coordinate system? Yep, negative Q0. Negative Q cosine theta, and then positive Q sine theta. Well, it's just opposite of what it was before. And now Newton's second law says, so we have the weight, plus the Q vector, negative Q cosine theta, positive Q sine theta. And then the normal force, 0n. And then the friction force, which this time is acting up the incline because we're trying to move down the incline. So that's mu n, 0, and all that's equal to 0. So the second equation says the normal is equal to W cosine theta minus Q sine theta. And now plug that into the first equation. So we have negative W sine theta minus Q cosine theta plus mu times the quantity W cosine theta minus Q sine theta is equal to 0. Distribute everything through. So we get negative sine theta minus Q cosine theta plus W times mu cosine theta minus Q times mu sine theta is equal to 0. And now I guess I'll get the W's on the left. So we have W times mu cosine theta minus sine theta is equal to Q times the quantity cosine theta minus mu sine theta divide both sides by cosine theta minus mu sine theta, and you get that Q is equal to W times the quantity mu cosine theta minus sine theta divided by the quantity cosine theta minus mu sine theta. All right, so this should have been plus, shouldn't it? So in this equation here, it should be Q times quantity cosine theta plus mu sine theta, and so that's the denominator two. So we got, it worked out the way I said it was going to work out, that we have a smaller thing in the numerator, bigger thing in the denominator, and so Q is smaller. Notice one thing here.
This actually could be negative in this case. It couldn't have been negative in the other case. What would it say if the numerator here became negative? And that would happen if this angle was big enough and or mu was small enough that sine theta was bigger than mu cosine theta. What would that say? That's right. Yep, exactly. That's saying that, I mean, the easiest way to think of it is that threading is getting so steep that the weight is just going to push the screw down to the bottom on its own. That's not a good screw design.
I've never heard that.
No. Any questions about that? All right. What you're going to have to do in the homework problems is just, instead of having variable, constants for all of these things, you're going to have numbers, but you're going to have to go through the steps of deriving what that force Q needs to be. Now we have to talk about the relationship between this Q and this theta that we're using in this calculation and real physical things that relate to those, which are the couple that you apply to the screw and the pitch or the lead of the thread. By the way, when you turn a screw, that is what you're doing. If you think of like a flathead screw, when you put a screwdriver in there and turn it, what you're doing is you're applying a force here that's equal and opposite to a force here, and a force here that's equal and opposite to a force here. And that has the effect of applying just a pure moment to that screw. The same thing if you have a screw, like if you think of a square-headed screw as like a jack to lift up your car, you put a handle on the end of it. That the easiest way to think of it is if you had a handle that extended on both sides, and you'd apply a force one way like that and a force one way like that, and again that just applies a pure moment to the screw. Okay, so what's the relationship? This is that number 2 thing I listed. What's the relationship between the couple applied to the screw
and the fake applied load Okay, well, first we have to think physically what that Q would mean. So if you think back, so first, what is Q? If you think back to that picture I drew of our sort of model of the screw thread sliding up the connected thread, it sort of looks like this. So that path there is the thread of the nut. You see that? And that force Q is the force that you would have to apply. Let me blow this up. Yeah, I bet I do, but I'm going to do it like this. But thanks for the advice on how to teach my own class. Okay. So that force Q, the idea is that we're going to get this thread to slide up the thread of the nut by applying a force straight to the back of this block, right? Or straight to the front if we're getting it to slide down. And so that Q is like this. The force going straight into the page in that picture. And so what we want, if we're trying to figure out the moment applied by this Q, because that's what we're trying to do, relate this to a pure moment, is we want to figure out the radius of this screw from the center to the thread, and we'll think of it as like the outside of the thread. And so that's actually the radius of the screw. So then the applied couple M is equal to Q times the radius of the screw. Or in other words, you could replace Q with M over R. Any questions about that? And then the last thing we have to talk about is the relationship between um, the pitch or the lead. So pitch or lead versus that angle theta. Most of the time, pitch and lead are the same thing. So if you think of a threaded screw, this distance here is called the lead. No, I have that backwards. That is called the pitch. The lead is, so to do the lead, I'm going to draw the same thing, and we're going to think about this ant climbing up this thread. That's a screwed up screw. Okay, so now we're thinking of an ant walking his way up. Looks like a little turtle. Okay, so he's going around, you know. The lead is the height change between the ant at one point to where he passes the same part of the screw his next time around. Okay. And so if the ant, you know, he's doing this, keeps going, he gets to the same part of the screw over here. This is the lead. And the lead is what's really useful to us for calculating that angle theta. Usually that's the pitch and the lead are the same thing. You can see the way I drew it here is the same thing. Square threaded screws, sometimes they make more than one track. It's called double threaded, I think, where they, so if you had this ant start here and keep going around, he would never end up on this thread. He would get back around on the other side over here. And then the lead would be that whole thing there. Okay. So they're only different in double threaded screws. All right, so how are we going to relate that height change? So this is L, pitch I'll call P. How are we going to relate that height change to the angle theta? Well, imagine taking that thread, you know, and removing it from the screw and stretching it out. what you would get is something like this. Where this is the angle theta we want. And this length is equal to the circumference of one time around. So this is equal to 2 pi r, where r is that same, the radius of the screw that we had before. This is the lead. Any questions about that? You follow that process? And so then the tangent of theta is equal to SOHCAHTOA L over 2 pi r. And so theta is equal to the inverse tangent of the lead over 2 pi r. Any questions about that? Okay. Let's do an example. Let's say we have a square threaded screw with a radius of 1 centimeter. And a lead that's equal to the pitch that's equal to 0.003 meters. Let's say that the coefficient of static friction is 0.2. And the screw is supporting a weight of 15,000 newtons. What couple is required to initiate motion up? Well, here's what we have. This angle theta is equal to the inverse tangent of 0.003. Oh, I didn't give a radius. Oh, I did. Okay. 0.003 divided by 2 pi times 0.01. Can someone calculate that? That's degrees. That has to, that's fine, yeah. 2.734 degrees, yep. And then we have a weight down of 15,000 newtons. Then what way are we going to apply the force Q. To the right, yep. Because we're trying to get this to move up. We're trying to fight against that 15,000 Newton weight force. And so this is our Q, and our Q is equal to M over 0.01. Which happens to be 100 M. Any questions about the setup yet? So free body diagram. We have the downward force of 15,000. We have the force to the right of 100 M. We have the normal force. And which way does the friction force act? Down the ramp, because we're trying to get it to move up the ramp. So this is 0.2 times the normal. A rotation matrix is cosine of that angle, 2.734. Sine of 2.734. Negative sine. Positive cosine. Can you calculate what those values are for me? Nine, 989, okay. Okay. And so the Q vector is that matrix, 0.9989. You don't, when you do these problems, you don't have to use the rotation matrix. If you like just thinking of it in terms of the trigonometry, that's fine with me. But I do think getting used to the rotation matrix is going to be a more and more useful thing as your classes go on. So 0.9989, 0.0477, negative 0.0477, positive 0.9989 times 100 M 0. And so that is 99.89 M, negative 4.77 M. And then that weight vector, it's this times negative 15,000. Can someone calculate that for me? 0.9989, 0.0477.
Negative 7, 15.5.
wait, 715.5, okay. Okay. So Newton's second law says 99.89 m, negative 4.77 m, plus negative 715.5, negative 14,983.5, plus 0n, plus negative 0.2n 0 is equal to zeros. Let's see. So this is a system of equations that says negative 4.77 m plus n is equal to 14,983.5. And the second equation says 99.89 m minus 0.2 n is equal to positive 715.5. Can someone solve that? And what are the units? Normal is a force, so that's newtons. What about m? Newton meters, yep. The order. I only did that because there's no reason. It doesn't change anything. I'm sort of used to doing it that way because if you do it by substitution, you first calculate n from the y and then plug it in. But if you're doing it as a system, it doesn't matter. Any other questions about that? Okay, so all this says that if you have to raise a car and then lower a car with a jack because you're putting a new tire on, it should be easier when you lower it. So now we know. We might have had a hunch before, but now we know. So that's good. All right, well, let's stop there. Next time, I'll get into belt friction.